Hello everyone. In this session, I'm going to look at making different kinds of basic financial calculations using R. We are going to look at the basic initial concepts like time value of money especially, right? Where we talk about present values, future values, annuities, etc. So NPV, IRR, different kinds of basic financial calculations, and how do I use the different kinds of R functions that are available to do all these calculations. So that's the major objective of this session. So we would have some amount of discussion regarding the interest rates, where we talk about the normal compounding of the interest rates, and we would also talk about the discount rate. What do we mean by interest rate? What do we mean by discount rate? How do I convert interest rate to a discount rate and vice versa? Then we also bring in the nominal as well as real rates of interest. The nominal rates of interest primarily, especially when we are talking about compounding frequencies, multiple compounding frequencies are there, right? Let's say the compounding happens twice a year or quarterly. Then what is the nominal rate of interest and what is the real rate of interest in that case? How do I convert from the nominal rate to a real rate and vice versa? Do I have any kind of R functions that are directly available for converting from a nominal rate to a real rate? The same logic holds true for discounts as well, not just for interest, even for discount. Do I have some kind of a function which can convert nominal rate of discount to a real rate and vice versa? Especially if the compounding happens monthly every year. Monthly means every quarter, every 6 months, every month, whatever it is. Then we would move on to understand another set of important concepts which we use for evaluating a lot of project decisions, wherein we would be talking about the NPV and IRR, net present value, and internal rate of return. Again, we'll see how we can use the R functions for accomplishing the same. Then we are bringing in the annuities. Annuities, we'll discuss about them, right? Generally, we are talking about equal installments to be paid at equal intervals of time. So those are typically considered as annuities. So how do I really get into finding out the values of the annuities, both the present value as well as the future value, otherwise called as accumulated value. So we'll be looking at that particular stuff. Now, as I said, in the definition of the annuities, we are talking about equal amounts to be paid at equal installments, equal intervals of time. But in some cases, that amount could be either increasing or decreasing arithmetically. So that those kind of annuities are being called as arithmetically increasing or decreasing annuities. So how do I find the present value or future value of those kind of arithmetically increasing or decreasing annuities? That's one more aspect that we need to look at. Similarly, in some cases, the amounts would be growing not in an arithmetic progression, but in a geometric progression, right? Probably 100. It would be increased by, let's say, 10%, 110, 121, 133.2, so on. So the annuity is growing at a geometric progression. If it is growing at arithmetic progression, 100, 110, 120, 130. So this is what it is growing in an arithmetic progression, the amounts. In this case, the amounts are growing in a geometric progression. So if they are growing in a geometric progression, how do I compute the present value or the future value? So those kind of scenarios also we are going to look at. Then the other aspect that comes in is deferred annuities, where the annuity is not starting immediately, but it is starting after a couple of years. So annuity itself is nothing but it's an equal installment in equal intervals of time. Now instead of starting immediately in the current year period itself, it will start probably a couple of years later. If that's the case, how do I compute the present value or the future value of that particular annuity? So we are bringing in those kind of calculations as well. Then once we have a conceptual understanding of all these things, we want to apply all these concepts to the regular financial scenarios in the real world, where I want to do the pricing of a bond. So I'll take a quick example to do the price of the bond. Then loan amortization. I want to take a loan. I want to compute the EMI, or not just the EMI. I want to make a complete schedule of the payments. So how do I do that in R? What kind of functions are available for me to accomplish such kind of stuff we are going to look at. And in a bond, one of the ways we talk about the risk of the bond is through duration and convexity. So these are the measures of assessing the riskiness of a series of cash flows. So how do I really assess the riskiness of this particular series of cash flows using duration and convexity? So these are some of the things that we want to look at as a part of this session. So let's get into one by one. Getting started with the interest rates. We know financial mathematics per se. When we talk about the word financial mathematics, we are dealing with time value of money. A dollar today is much worthy compared to a dollar that I receive in the future, let's say after 1 year. The same $1. Because the $1 that I am having today, I can invest it for 1 year at some interest rate, and I will get something more than 1 at the end of 1 year. So which is a clear indication that with the passage of time, the money is increasing in value. That is what we are calling as the time value of money. So as a simple representation, if I am talking about an amount X, I have invested it for T years, and every year my effective rate of interest is I. We use the word effective rate of interest. In effect, every year I am getting an interest rate of I. That is what I am calling as effective rate of interest. So if that is the case, with the help of compounding that is happening, I am going to receive x into 1 plus I to the power t based on the compound interest formula, right? So this is a very simple calculation. If I have deposited x amount for t number of years, and per year the effective rate of interest is I, I'm going to receive x into 1 plus I to the power t at the end of t years. So this I is very important for us because we are dealing with interest rates. This I is called effective rate of interest, which is as good as saying, so if I'm talking about this as one single period, let's say in this case take it as an year. So I am depositing one. I'm depositing 1 at the beginning of the period. How much will it become at the end of the period. Let's say at the end of the period it becomes 1 plus I. Now this I is what we are calling as the excess is I. This I is what we are calling as effective rate of interest. So that one single unit, when I am investing at the beginning of the period, what will it become at the end of the period? That excess that I am getting during the period is what is typically called as effective rate of interest. Right? 1 becoming 1 plus I at the end of the period is what is my effective rate of interest. So the interest here is I, which I would be receiving at the end of the period. But if I have to talk about the same, right, what is the present value of this I? This I is going to come at the end of this period. But as of today, what is its worth? If I want to find out what is the worth of this I, as of today, it's as good as I by 1 plus I. I'm finding the present value as of today, right? So the present value is I divided by 1 plus I, which is otherwise called as the discount rate. So if that amount I has been earned today itself, at the beginning of the period itself, right? Because if you see, I is coming at the end of the period, right? Okay. So now I'm talking about some x value into 1 plus I is equal to I. Some x. So now I am computing this x, because this x with an interest rate of I at the end of 1 year is becoming I. So based on this I am computing this x, which is I by 1 plus I, which is otherwise represented as D and is also called as the discount rate. So the present value of the interest that I am going to receive at a future date is what we are calling as the discount rate. Now, once I know the interest rate, I can convert it into a discount rate, or once I know the discount rate, I can convert it into an interest rate. For doing all these things, we are working with a few packages in R. So for doing all these calculations, which I am dealing in this particular session, I'll use a package called live contingencies. This is the name of the package that I'm going to work with, which contains a lot of these financial mathematics related calculations. So let me do one thing. Let me install that package. Live contingencies. Okay. So this is the package that we are going to work with for computing our interest to discount, discount to interest, etc. So remember, discount is nothing but it's the present value of the interest that you are going to receive at the end of the period. Right? So library live contingencies. So we are loading this particular package. Done. Right? So now let's do the quick calculations using this package. See, typically, if I want to do interest to discount conversion, actually speaking, I can simply use this formula, right? I equal D equal to I by 1 plus I. So I really don't need it, but yes, let's try to understand the formula. interest to discount. If you try to look at this particular formula, so this function switches from interest to discount rate and vice versa. That's nothing. It's just a very simple job. But initially, for us to understand what is typically going in, so we are looking at the usage. Similarly, discount to interest, I get the discount rate, I get the interest rate. So let's use this interest to discount of 5%, which is 0.05. So it says 0.0746. So when I'm converting it into a discount rate, it is 4.76%. Similarly, discount to interest, the same number, but the only thing is conceptually I have to be clear what I need to convert to what. So discount to interest again is taking that number back to 5%. So let's say I'm investing 100 for a period of 2 years, right? I'm investing 100 for a period of 2 years. So at the end of 2 years, it is coming out to be 110.25. So now, if I have to bring it back to 100, all I can do is 110.25 divided by 1.05 whole square. So, or I could simply take it with respect to discount. 110.25 multiplied by, first of all, I have converted interest rate into a discount rate, right? So I can take it as the interest to discount 1 minus d square. Even this is taking me back to 100. So you could see a few conversions out here, right? So what we have done, x into 1 plus I squared is equal to y. 100 into 1.05 squared is equal to y. So x would have been simply y by 1 plus I squared. But we have known that d is nothing but I by 1 plus I. Right? I want to use this relation. So I by 1 plus I, which is otherwise, I could have written this I as 1 plus I minus 1 by 1 plus I. So which is also making 1 minus of 1 by 1 plus I. Now this is what is typically being used. So instead of saying y by 1 plus I squared, I have made it as y 1 plus I squared. Now this is d, right? D equal to this. So 1 by 1 plus I is nothing but 1 minus d. So 1 by 1 plus I squared is nothing but 1 minus d squared. So I could convert one into other by having a basic understanding of the concepts. So we have converted interest rate into a discount rate into an interest rate quite comfortably. That's the first part of understanding. Then, in not necessary, in all the cases, the interest will not be paid annually itself. Right? In many cases, probably if you look at the banks, they pay the interest rate quarterly into your account. So the interest is paid not necessarily on an annual basis. Even the reinvestment of the interest, not necessarily on an annual basis, it could be more and more frequent than once in a year. So that particular period, so if it is done quarterly, then it is 4 times in a year. So that is what we say, the interest is computed or compounded quarterly. But whenever it is expressed whenever it is quoted, right? The conversion of it could happen every quarter. The compounding of it could happen every month. But when I'm quoting it, when I'm showing it to the customers, I would use this quoted interest rate itself. So I will express it in nominal terms. So the bank might say, for this fixed deposit, the interest rate is 8%, but they may compound it quarterly. So they will not give me an effective interest rate which I am going to get for the year. They are not going to talk about the effective interest rate. So they will quote it as the quoted interest rate, otherwise called as the nominal interest rate, and they would also specify the convertible term. So they may say 8% is the quoted interest rate, but it is compounded quarterly. So the convertible terms IM is 8%. But what I actually get, so it doesn't mean that if I am depositing 100, I will get 108 at the end of 1 year. This is annual compounding. But if it is saying I4 equal to 8%, it means that the nominal rate of interest is 8%, but it is compounded quarterly. So what I am going to get is nothing but 1 plus 8% by 4. This is actually the quarterly interest rate here. So the nominal interest rate divided by the number of periods of conversion to the power of the number of conversion periods during the period. So which is what might result in something greater than 1.08 itself. But which means an effective rate may not be 8%, it may be 8.2%. But the bank cannot quote it as 8.2%, they'll still quote it as 8% itself. So the effective rate of interest earned in the conversion, so whatever is during this period, the effective rate of interest during the quarter, the effective rate of interest is 2%. Right? So the way we are talking about the nominal is, if I am talking about quarterly compounding, the effective rate of interest every quarter is 2%. So this 2% multiplied by 4 is what we are calling as the nominal rate of interest. But understand, the interest that came here will carry another interest here, will carry another interest here, will carry another interest here. So the effective rate of interest for the whole 1 year is different. The effective rate of interest for this single period is different. So it's better that you remember this particular equation. When we are talking about annual rate of effective annual rate of return, 1 plus I to the power t. But if we are talking of mthly compounding, it is 1 plus Im by m to the power t. Right here I should use mt, whatever is the time period. So similarly, the same when you are using it with respect to discount rates, so it will go the other way. 1 minus dm by m. So we are talking about the discount rate, annual discount rate, right? So 1 plus I to the power t, I have already said, with the usage of some expressions, we have already said d is nothing but 1 by 1 minus 1 by 1 plus I. So based on this, I can say 1 by 1 plus I equal to 1 minus d. So 1 plus I is nothing but 1 by 1 minus d. So these relationships you need to have a comfort level. So I can very well write it as 1 by 1 minus d to the power t, which is other way of writing 1 minus d to the power minus t. Now the same thing, D is like a annual rate of discount. But if the discounting is happening every period, mthly conversion, I can write it as dm by m to the power minus t. Here the t is in terms of number of periods. Sometimes we denote with the notation V. I equal to I. V is nothing but 1 by 1 plus I. So we know D is nothing but I by 1 plus I. So sometimes it becomes IV. Right? So that's the reason with this, when I'm writing it as V to the power of minus T, it is nothing but 1 by V to the power of T, which is also nothing but 1 plus I to the power T. Right? So these are different kinds of notations, but yes, if I have to convert from one form to the other, understanding of these notations become more and more handy for me. So let me look at the conversion between the nominal rate and a real rate. Nominal, we have already got a clarity now, right? Real is what I am calling as the effective rate of interest for that period. Right? Nominal is wherein the compounding frequency I'm not considering. It's only per period effective rate. So if the easiest way to understand is, so if I take per period effective rate and multiply it by the number of periods, that is what I am going to get as the nominal rate. But if I take the compounding for each of the periods into consideration, not just a simple multiplication, but compounding also into consideration for each of the periods and compute the net amount at the end of the period, that is what we are calling as the effective rate of return or the real interest rate. So I can use this function called nominal to real. Let's see what this function is doing for us. Nominal to real. You see this? This function provides convenience functions to switch from effective to convertible rate. So from an effective rate, which is like a real rate, I am looking at convertible rate. So now you could see nominal to real. So the nominal, I am giving the interest rate, which is the rate that I want to convert. I can also use real to nominal. Okay, first let's look at nominal to real. I is the rate to be converted. Then K, the original target compounding frequency. So what is the compounding frequency that I am looking at? So if I set it 4, then it means quarterly compounded, 12 means monthly compounded, and so on. And the type, if I am setting it as interest, it would do on the interest rate. If I am setting it as discount, it would give me the discount rate. So that is what is the type talking of. That's it. So I can very well convert this stuff nominal to real. So let me do nominal to real. If I'm talking about an interest rate of, right, let's say 10%, 0.1, then I'm talking about a compounding frequency of quarterly. So I'm setting it as 4, and I'm talking about it as type equal to interest. So it's as good as saying, if I have to convert it into real, oh, let me redo it. I did not close the quotes. Yeah. So it becomes the same 10%. If I'm talking about a quarterly compounding, it is going to become 10.38%. Right? So that is what is the quarterly compounding part. Now similarly, if I want to do the other way, I'll say real to nominal. I'll say real to nominal, everything remaining the same. This time my I is going to be the real rate. So this is the effective rate for the whole year. I want to find out what is the corresponding what is the corresponding nominal rate of interest if I'm talking about a quarterly compounding. So the real to nominal is again taking me back to 10%. But the same thing, if I want to convert in terms of discounts, right? Let's say I want to use nominal to real. Instead of interest rate, I'm talking about the discount rate. Remember, it is nothing but instead of I am taking it as D. So this becomes 0.9096, which is 9.63%. When I am converting this as the discount rate, nominal discount rate to a real discount rate, it is becoming 0.9096, which is 9.63%, right? Which is otherwise we are having a D as zero point 0.1. Now I am converting it into 1 minus, we are talking about D4. The D4 is going to be 9.63%. Then if I am talking about real to nominal, again the same logic. I equal to, I'll take it as 0.0963. Then I'm taking k equal to 4 and type equal to discount. So again I'm getting back my 10. So we need to be comfortable in terms of using when to convert it from nominal to real, when to convert from real to nominal in all these kind of examples, right? And when to use interest rate, when to use discount rates. Then the other important concept in this context is the concept of present value. We have a series of cash flows, right? We have a series of cash flows which are going to come at different points in time. Different amounts are going to come or I need to pay at different time periods. The interest rate is known. So the interest rate, I need it as an effective rate of interest. We'll look at it. For this particular period, I am looking at the effective rate of interest. So I have known cash flows at different points in time. These are the interest rates and these are the probabilities. In some cases, the cash flows that I'm going to get, there may be a lot of uncertainty in the cash flows. Let's say I will get those cash flows only if the project is successful. If it is failure, I will get some other amount. Or I will get those payments only when the person is alive. When the person is dead, those cash flows are not going to come up. So there could be some kind of cash flows which are based on a contingency. So that is where the probabilities are typically being considered. So once I have all this information, how much cash flows I am going to receive, at what points in time, because any investment that I am making, remember or look at it with slight more criticism, any kind of investment that I am making today, I am going to receive some kind of money in future, right? In many cases, the amount that I am going to receive in different kinds of instruments except the fixed deposits, so the amount that I am going to receive and or the time that at which I am going to receive those amounts, there will be a lot of uncertainty. So in finance, we are all dealing with uncertainty itself. So the amount that I am going to receive or the time at which this particular amount I would be receiving, they are all uncertain. So when we are talking of uncertainty, there is a scenario of probability that is coming into picture. What is the chance that that amount would be received? Then we are talking about the interest rates for each of the periods. So those future amounts that I am going to receive, I'm going to compute the present value of all those future amounts, right? I'm going to find out the present value to really see if the investment that I'm making is a profitable investment or not. So I can have a direct formula called present value. I'll have a formula called present value. Evaluates the present value of a series of cash flows. So I can give a series of cash flows, I can compute the present value given the occurrence time. So at what time the cash flows are going to come. So I can compute the present value of a series of cash flows given the occurrence time. The probabilities of occurrence can also be taken into account. So if there are uncertainties with respect to cash flows, even those can be considered as a part of the model. So I'm giving as an input the cash flows. It's a vector of cash flows. So the only thing is it should be coherent with the time IDs. So the number of time periods that I'm giving, the cash flows for each of that time period needs to be provided. Time ID, vector of points in time where the cash flows are due. Then the interest rate, a numeric value or a time size vector. Either I can give one single value or I have to match it with the number of time periods that I am giving. So if for each period I have a different interest rate, then I can give it again as a vector which is of the same size of the time IDs. Then the probabilities are typically the optional where which talk about what is the probability of receiving each of these cash flows. So I have to give all this information for doing this computation. So let's do this numerical which I have written down. Find the present value of 1000 to be paid at the end of 6 years at 6% per year payable in advance. So this is the amount that is payable in advance and convertible semi-annually. So actually what I am being given is D2, right? 6% per year payable in advance and is convertible semi-annual. So the D2 is being given as 6%. But the present value I will always compute with respect to I. The interest rate is always I. So this D2 I should be first of all converting it into D, and this D I should convert it to I and then use this I for computing the present value. So we have to be very careful what is being provided to us. So the D2 is 6%. So I will convert it into D first of all, right? So I can very well say the D, which is the real discount or effective discount. So let me call it as ED, which is the effective discount rate. So because I want to find out the effective discount, I can convert it from nominal to real. I'll say nominal to real. I equal to, what is the discount rate? 6%. So 0.06. K equal to 2. We are talking about a semi-annual compounding and the type is coming out as a discount. So this will give me the value of D. D2 is being provided. So from D2 I am computing the value of D. Now from D I have to convert it into I. So basically I'll call it as effective interest, or probably I'll convert it just to I, which is nothing but now I am doing discount to interest conversion. Discount to interest. I am doing a discount to interest conversion wherein I am providing the ED which I have got as nominal to real conversion. I am giving that as an input to discount to interest. So this is what is my I. So if I'm looking at this I, it is around 6.28%. So from the discount rate, I have converted it into, now if you look at ED, it is 5.91. So from the D2, which is a nominal discount, I have converted it into an effective discount, which is 5.91. From the effective discount, I have converted it into an effective interest, which made it 6.28. Now I can find out the PV, which is the present value, by using the present value function. Present value, where what are the inputs that I have to give? In the present value function, I have to give these inputs. So let me give cash flows. So anyhow, it's one single cash flows, but if we have multiple, I'll show you what to do. We can use them in the C function. So I'm setting cash flows equal to 1000. Then I have to give time IDs. Time IDs is equal to, for how many years? We are talking about 6 years. So all 6 years I'm going to get the same cash flows. Right? At the end of 6 years I'm going to get the cash flow. Then the interest rate, I can give the interest rate is fixed, which is coming out to be my I, which is 6.28%. And probabilities, there is no uncertainty in the cash flows, so I can very well set the probability is equal to 1. Even if I ignore it, it's going to take by default the probabilities as 1 itself. So this is giving me my PV value as 693. So it's as good as I could have done 1000 into 1 minus of 0.06 by 2 to the power 6 periods. 2 compounding is done. So I could have done something like this. 2 into 6, 12. So making it 693. But yes, if I'm going in a streamlined fashion, it would be much more appropriate without any scope for errors in the calculations. Right? Now, moving on to the next topic, where we are looking at net present value. Right? We have found out the present value. Now we are talking about net present value, which means generally when we have a few outflows, right? Generally we invest in projects, so there are outflows, and those projects will start yielding some cash flows in the future. Those are inflows. So when we are talking about the net of outflows and inflows, and I'm trying to find out the present value of both the outflows as well as inflows, and finding the net value. It could be a positive. If it is positive, means net inflows are higher than the outflows. If it is negative, means outflows are higher than the inflows. So when the outflows are higher than the inflows, obviously it's not a profitable investment. So I should not invest in that particular project. Whereas if it is the other way, if the net inflows are positive, net flows are positive, then I should look at investing in that particular project. So that's how I can talk about the net present value. So we are talking about a series of cash flows at different points in time, and a few of them are inflows and a few of them are outflows. And the net of it, when I'm trying to find out, that is what we are calling as the net present value. Very, very important feature to evaluate the whether a particular investment should be accepted or rejected. When the NPV is positive, we will accept that investment. When it is negative, we will reject that investment. And now if you see the formula, we are going to have different cash flows at different points in time. So at period 1, whatever is the cash flow that I am getting, I'll discount it with the interest at period 1. Then if I am getting some cash flow in the second year, I'll discount it with the interest of that particular period squared, and so on. So this is how I'm getting my NPV. So manually I can very well simplify each of these things, and that is what can give me the computation. But I can very well solve using the same present value formula that we have used earlier. I can solve the numericals associated with the NPV as well. If you look at this example, we'll take it up. Which investment strategy is preferred between A and B? A is having, I'm investing 500 now, so the investments I'll take it as a negative cash flow. So the time period 0, I have invested 500. This is what is my project A. At time period 0, I have invested 500. Receive 100, 200, 300, 250 at the end of the following 4 years. So at the end of 1 year, I am receiving 100. At the end of 2 years, I might receive 200. 3 years, I will receive 300. And at the end of 4 years, I am receiving 250. This is how this investment of 500 is going to fetch these cash flows for me in future. So these are all estimated numbers only. So I need to have a good amount of understanding of my project so that I can estimate how much cash flows I am going to get in the future. Then I have a B which says you invest 700 now and you receive 1000 at the end of time 2. So these are the two projects that are available with me. So here it is 0, here it is 0, all these are 0. So lump sum I am going to get 1000 at the end of year 2. Now what we are saying is which out of these two projects are more and more comfortable, right? Which one I should go with? If I have NPV as a decision criteria, if I'm trying to make my decisions using NPV, which of the following projects do I need to take up? If you remember the kind of present value formula that we have used, it requires all the cash flows. So I have to specify the cash flows. It requires the times at which I'm going to receive those cash flows. So I have to specify the time. Interest rate, here the interest rate, I can make some kind of an assumption regarding the interest rate. So let's take it as let's say 10% or 8%. Let's take the interest rate as 8%. And the probabilities, now we don't have any kind of doubts regarding the future cash flows here, so I can take the probabilities as 1. So let's go ahead. So first I require the cash flows. Either I can give in one single formula itself. So let me call NPV1, the first NPV for the first project, or probably let me call it NPVA. The project A, I'm looking at the NPV where I'm using the formula present value. The first thing, cash flows. Right, the cash flows, instead of directly giving 1000, if it is the same amount I could have given it as something like this, but here we have different cash flows in different periods, so it's better that we use a C function. So the first one is minus 500, then it is 100, then it is 200, 300 and 250. So we have taken these as the cash flows over each of the periods. Then I have to give the next input as time IDs. Time IDs, I will set it as each of the periods. So because I have given 5 different cash flows, I need 5 different time IDs. So because they are in a sequence, I will give it as 0 to 4. So it will take the values 0, 1, 2, 3, 4. Then the interest rates, if they are different, fair enough, I have to give them separately. But for this entire period, my interest rate is 8% only. So I am simply taking it as 0.08. And probabilities I can ignore because there is no uncertainty in the payment, or it's as good as I am giving probability as 1. So this is how I am getting my NPVA. Time IDs, probabilities must have the length of cash flows. Okay, so probabilities again must have the length of cash flows. So probably I should put it as a sequence from 1 to 1 increment by no, I can't put so let me say we'll repeat it, repeat 1 5 times. So that is what we'll set it as probabilities. Otherwise I could have ignored the probability. So we are repeating 1 5 times. So that is where I am setting the probabilities as equal the length same as that of cash flows. So based on that, I'm going to get my NPV for the project A, which is working out as NPV A is telling me that the number is 185.96, right? So for this project, the NPV is 185.9675. This is the NPV for this project, and because it is a positive one, I can very well take up this project. Whereas now let me see for the project B, NPV B, just a quick revision. So I am using the present value function. The cash flows this time, there are only two cash flows, remember. So the one is a negative cash flow of 700, then there is a positive cash flow of 1000. Coming to time IDs, I have only two times. One is a time period 0, the other is 2. So that's the reason I am not giving it as a sequence. The interest rates, they are common across the whole period. The interest rate is 8%. So I am setting it as 0.08. And probabilities, again I can very well set it as repeated 1, repeat the number 1 2 times. So with this I can very well find out my NPVB, what has actually happened. Cash flows, time IDs, interest rates. Oh, I have to, in time IDs I didn't give a C function. So give a C function. So my NPVB is computed. So NPVB is coming out to 157.33. In the second case, the NPV is 157.33. So because the NPV, now both the projects are good enough projects because the NPV is positive in both the cases. So anywhere where the NPV is positive, that particular project can very well be taken up. But what we need to understand is if I have to really pick up only one single project out of these two, right? Sometimes called as mutually exclusive projects. So if I take one of them, I cannot take the other one. So if the projects are mutually exclusive, though both the projects are equally profitable, I cannot take up both of them. I have to take only one. In that case, I would prefer this first project because it is having a higher NPV compared to the second project. So that's how we can use NPV for the decision making purposes. The project that is having the highest NPV would be preferred for the investment purpose. Then on the same lines, just like NPV, sometimes people also use another mechanism called IRR for evaluating the projects. IRR is nothing but the internal rate of return. Okay, here if I want 8% in NPV, what is that we are saying? I want an 8% return. Based on this 8% return, what is the present value of both the projects? So I as an investor, my expectations, my expected return is taken into consideration for computing the NPV. So I require, so this 8% is called as the required rate of return. I as an investor, I require 8% return on any investment that I am making. So considering this 8% as the required rate of return, the NPV is computed as this and this. But now in IRR what happens is I will not consider the investor's required rate of return. In turn, I will see what is that minimum rate of return that makes the project break even. So which means what is that particular rate of return where the NPV is exactly equal to 0? What should be? So instead of 8%, if it becomes 10% or 15% or what it is, if the required rate of return is 15%, will the NPV be still positive? If the required rate of return is 20%, will the NPV still be positive? So what is that rate of return where the NPV will become 0 is what we are calling as the internal rate of return. So in short, okay, if we are investing this much and we will get this much, what is that rate of return that we are getting over the entire period? What is that annualized, what is the effective rate of return that we are going to get during this entire period when we are investing this amount and receiving these kind of cash flows in future? So that's where people call this as the inverse of NPV. So instead of specifying an interest rate, we would be deriving that particular interest rate where NPV becomes 0. That particular rate of interest where NPV becomes 0. So that's the typical process we do for solving also. We create a function wherein I'll use the present value computation and I'll set the present value to be as minimum as possible. That's the reason I take present value should be 0. So I would be iterating through the process. So because we don't have, we have to do it the trial and error way. What we generally do is we create a minimization function. We create a kind of a function wherein we are taking the NPV value. We take the NPV squared. So NPV equal to 0 means NPV squared is, instead of taking it as 0, we'll say let it be as minimum as possible. So do an iterative process. We will talk about the minimization, the non-linear minimization. We can use a quadratic minimization. So we'll use non-linear minimization process to typically make sure that this NPV value, NPV squared value, because if I take NPV and say it is 0, it could be either negative or positive. So that's where I am taking a square of the NPV and trying to see this, the squared value should be as much minimum as possible. And for using this minimum, I'll use this nonlinear minimization function. So which will typically compute the value of IRR for me. So this is how the function I'm writing. I'm writing a function with IRR as the input. And we are finding the present values wherein we are giving the cash flows. The time IDs we are giving, which are already known. So I'll take the same example and compute the IRR. The interest rate that we are supplying is this IRR. So this particular IRR is computing me the NPV using the present value function, and I am making sure that this NPV squared will be 0, and for that I am trying to find out what should be the value of IRR, and that minimize the that value, equating it to as minimum as possible. I am using the NLM function, which is nothing but the non-linear minimization. So for the same examples, I want to do the IRR. So first let me compute a function f, which is a function of IRR. So whatever the function f gives me, that is what is the IRR that we are trying to use. So we'll use this formula, present value. We'll compute this present value of the cash flows, whatever I supply as the cash flows. So let's make it general. So I'll supply the cash flows to it as some CF. I'll take some CF. So I'm supplying some cash flows. Then the time IDs also I can specify. So let me call them as TI, the time IDs, and the interest rate. So this is what I'll take it as IRR, and this gives me the NPV. This whole thing will give me the NPV. I'll do the square of this NPV, and this is where I'll close the function bracket. So my function is taking IRR as the input, some value, right? I'll give, so based on the cash flows, based on the time IDs, this function will take IRR as the input, some rate of return as the input, and it will compute the present value. I'm squaring it. Now I want to minimize it, right? So for minimizing, I'll use a function called NLM. See what it is doing. NLM is carrying out a minimization of a function. So my function here is NPV squared. That is the name of, that is the function that we are using. We are using NPV squared. I want to minimize that particular function using a Newton type algorithm. So all I need to give is the function. I have to give it as one of the inputs to this, and the starting parameter value per minimization. So what should be the value for this IRR? So let me take it as 1% or something. I can take the starting value for the minimization purpose. So with those two inputs, right, but I have to give the cash flows first of all. So let me take the first numerical, wherein I am giving the CF. For the first numerical, my CF is, I can take these numbers as my CF, right? Then I can give my TI as 0 colon 4. This is the first example I am talking of. So based on this, I can say IRR of the question A is nothing but, now I can very well use NLM, right? Where initially the function that I am giving to this NLM is F, and I'm saying initially you start off with 0.01, which is 1% or something. Start off with 0.01. So first let me execute, right? Let me tell you, as before assignment, let me just do NLM f comma 0.01. See what it is doing, the NLM function. If you simply say NLM f comma 0.01, it gives a few things. The minimum value it is giving. By doing this NLM nonlinear minimization, I am getting the minimum value as 2.927. I am getting the estimate value. This estimate is nothing but the IRR value. So I am getting that. I am getting the gradient, which is the slope, then the code and number of iterations it has typically taken. So what I really need as an IRR is this estimate. So this is where I say, when I am saying IRR in case of A, I'll always say NLM. Whatever is the NLM that we are executing, let's say using 0.01, I will take the estimate value of that, and that is what will be my IRR A. So in the first case, the IRR is coming out to 21.47%. So for this example, the IRR is coming out to be 21.47%, which means as long as, I mean, when the investor was having 8% required rate of return, this is a profitable project. Even if he has 10%, this would be an acceptable project. Even if he has 15, 20, up to 21.47% requirement, this project would be an acceptable project itself. But once the investor's requirement goes much above this 21.47%, let's say if the investor's expectation is 25%, then the NPV of it will become negative. So then the project would be rejected by the investor because he wants 25% return, whereas this project is capable of generating 21.47% return. So as long as the IRR is greater than the required rate of return, which is demanded by the investor, this project will be an acceptable project. So this is what generally we call as the cost of capital. Required rate of return, we otherwise call as cost of capital, means the person who is providing the capital for this project, he wants this much of return for the investment that he is making in the project. So as long as the project is going to give a much higher return than the what is required by the investor, this project can quite comfortably be taken up. So this is a project which is giving me 21.47% return. Quickly, if you execute the same for the second, my CF now is becoming minus 700 comma 1000. This is the second numerical that I am taking. TI is becoming C0 comma 2, right? And now I can very well use IRRB, which is nothing but NLM, nonlinear minimization is what I am trying to do. This function I want to minimize. I'll start off with 0.01 itself and I'll take the estimate of whatever it is typically giving. So if I look at IRRB, it is saying it's 19.52%. This particular project, on an average, it's giving me an effective return of 19.52%. So this one is giving me a higher return compared to this particular project. So even if I'm using IRR as a decision making criteria, I would typically be preferring the project 1 because it's having a higher IRR compared to the project 2. So generally for making decisions regarding the investments, people use NPVs and IRRs as the criteria. So the higher is the NPV, the project would be having a higher chance of getting accepted. The higher is the IRR, the project will have a higher chance of getting accepted. So that's how the NPV and IRR play an important role in the investment decisions, especially if the cash flows are coming over longer periods of time, right? Then, now that single cash flows and multiple uneven cash flows have been looked at, the next important point I want to bring in is the annuities. So as a definition, again, in case of annuities, there are two things I am interested in computing. What is the present value of these annuities and what is the future value of these annuities? And in the future value, generally we sometimes use another term called accumulated values. So we can use either of these calculations when we talk about the annuity. First of all, conceptually, annuity is a series of payments, so it's not one single payment. It's a series of payments generally happening at equal intervals of time. So at the end of 1 year, 2 years, 3 years, 4 years. So it's a series of payments that are being made at equal intervals of time. In many cases, the amount also could be equal amount. So when I'm talking about the same amount paid across equal intervals of time, that's a traditional definition of annuity. So within that, we have different kinds of annuities. One is annuity certain. Terminologies that we need to be comfortable when we are working with annuities. One is annuity certain, saying I'm sure that I'm going to receive those amounts. So we are talking about different payments or different receipts that are happening. So here we are talking of either payment, which is a cash outflow, or receipt, which is a cash inflow, whatever it is. So if they are bound to occur at different periods of time, and if they are guaranteed that I will get them, then we are calling them as annuity certain, which means the probabilities are typically 1 in these cases. So there is no uncertainty associated with each of these payments. So there is no risk that is involved with respect to the paying or the receiving with respect to these payments. Then another couple of words that are important in this context: annuity immediate or ordinary annuity. We are talking about regular annuity. There are different words to it, or ordinary annuity or annuity immediate. So there are so many words for it, right? So there are so many words. Okay, the immediate or regular or ordinary, wherein we are talking of the payments or receipts at the end of the period, right? So when I'm talking about doing a valuation as of this date, this is the end of the first period, end of the second period, end of the third, end of the fourth, end of the fifth. So if I'm talking about the payments or receipts occurring at the end of each of the periods, we are calling it as a regular annuity. But if the payments are done at the beginning of each of the period, that's the only difference. We are talking about payments at regular intervals of time. But if the payments are done at the end of the period, at the end of each of the periods, we call it as a regular annuity or a ordinary annuity. But if the payments are typically happening at the beginning of each of the periods, we are calling it as annuity due. So we have to be very clearly seeing where the payment is typically getting made. Is it made at the end of the period or is it made at the beginning of each of the period? So depending on that, our formula will differ slightly, right? So a clarity, this is again a clarity in terms of when the payment is typically getting made. Now, when we are talking about this particular annuity, we can find out the present value of all those future cash flows that we are going to receive at the end of each of the periods. So the present value is generally represented with this term AN. So which is nothing but it's an annuity, regular annuity. Up to n periods, I am going to receive an amount of 1 at the end of each of the periods. So if I am receiving an amount 1 at the end of each of the periods, then what is the present value of all those ones that I am going to receive at the end of each of the n periods? So generally the formula will come through this mechanism. But yes, once we understand the concept in R, the formula is a straightforward formula. I have a formula called annuity. So it can do the computations of both ordinary annuity. The same formula annuity can do the calculations for ordinary annuity, can do the calculations for annuity due, and many more things. So we have to be slightly understanding the whole formula of annuity so that we can use them quite comfortably in our calculations without getting that confusion. So let's use the word annuity. It's a function to calculate the present values of annuity certain. So I can calculate the present values of annuity certains, no uncertainties that are involved with respect to the payments. So I can use the annuity function to compute the present values of all those certain annuities. Now if you see the input, the first input that I have to give is I, effective interest rate. Right, so I have to specify what is the effective interest rate in a decimal form. I should not specify it as 3%. I have to give it as 0.03. Again, if for all the entire period the interest rate is same, I can give it as one single value. But otherwise, I have to give it as the vector of interest rates. So depending on the how many time periods I am giving, those many interest rates I need to have. So that is, so if each period is having a different interest rate, I have to specify it that way. In many of our initial calculations, we may have one single interest rate itself. Then we need to provide N, which is the period for payment. So how many years this particular annuity is going to be paid or received? What is the period of this particular annuity? N number of periods. So if I'm setting N as infinity, then that particular annuity we are calling as perpetuity. If N is infinite, so generally we are talking about payment for 10 years, 15 years, then they are regular annuities. But if N is set as infinite, which is forever kind of stuff, we are calling that annuity as a perpetuity. Forget about whether it's an annuity due or a regular annuity. But if the payment is typically being, if the time period is for n years, for infinite number of years, we are calling that as a perpetuity. Then m equal to 0. So m is the differing period. So at a later point I'll take up this example. But the annuity is not starting in this current period itself, but probably after a couple of years. So annuity is equal payments at equal intervals of time. If that equal payments are starting from this current period itself, we are calling them as a part of regular annuity. But if this process starts after a couple of periods, right? Initially for the next 2 periods there are no payments. From the third period onwards, every period you have to pay this much. In that case, we call it as a deferred annuity. So we have to specify the deferring period. If you don't specify it, the default value is taken as 0, saying the payment is immediate. So it's not deferred. In this period itself, there is a payment that is happening. Then we are talking about K, which is yearly payment frequency. How frequently we are paying in a particular year. So if it is 1, it means that the payment is being made at the end of 1 year itself. So we are talking about the number of payments that, within a year, how many payments are we typically making? So that is the yearly payment frequency. And finally, the type. I will set it, if I set it as immediate, it will be an immediate annuity. If I am setting it equal to due, it would be an annuity due. So almost all the problems can quite comfortably be computed with this particular formula. All the present values of the immediate annuities, annuity dues, lot of these calculations can be done straightforward here. So let's take up a few examples which can help us in solving these numericals quite comfortably. Compute the prices of this following annuities. Calculate the present value of an immediate annuity. Okay, I have to calculate the present value of an immediate annuity. Amount of 100. So the cash flows is 100 for each of the period for 5 years. So we are paying 100 for 5 years. So the N for me is 5 at the rate of interest of 9% per year. So I is coming out as 9%. So I could directly use the formula as well, right? Whereas I can directly use the annuity formula also. So the cash flow, I will directly take it as a multiplier. So the numerical 1 for me is working out as 100 multiplied by, now I will take the annuity value. So annuity, the first input in the annuity function I have to specify as I, which is the effective interest rate. So let me take my I as 9%, which is 0.05. Then I have to give N, which is the number of periods which this annuity is going to continue, which is 5. M, there is no differing period, so I can set it to 0, otherwise it could, it will by default it will take as 0. K, the yearly payment frequency, here the payment is made only once in a year. So I don't need to bother about it. I can even ignore it. The default is k equal to 1. And then I am looking at type. So because this is an immediate annuity, I am setting it as immediate. But if it has been an annuity due, I will set it as annuity equal to due. So I have got my N1 value, which is the numerical 1, is saying that this value is 388.96. 388.96. So what does this mean? If you are depositing 100, if you are paying 100, right? So let me put it like this. This is time period 0, which is today. 1, 2, 3, 4, 5. So at the end of the first period, right, from here is the first period. So at the end of this first period, I am paying 100. End of second, another 100, 100, 100, 100. So these are what I am typically paying. I want to find out what is the present value of all these future payments that I am making, which comes out to 388.96. It's as good as saying if you deposit 388.96 today and the annual interest rate is 9%, it's very much possible that you can withdraw 100 every year over the next 5 years. So the present value of that particular annuity is 388.96. Now look at the next numerical, which says suppose the company issues a stock that pays a dividend at the end of each year, so which means it's an immediate annuity. The payment is being made at the end of each year. The amount that is being paid is 10 indefinitely, which means it's a perpetuity. So the n I can set it as infinite. The company's cost of capital is 6%, so the interest I can very well take it as 0.06. What would be the value of stock at the beginning of the year? So we are talking about the present value. So in case of N2, let me give the information. In case of N2, I am saying 10 multiplied by the annuity of I in this case is 0.06. The N I am taking it as infinite. Then there's no deferment period. It's only once in a year. So even that I don't need to bother. The type is immediate. So let's see what is the present value of this, which would work out to be the value of the stock at the beginning of the period, which works out to 166.67. So if a company is going to pay a dividend of 10 bucks indefinitely and the cost of capital is 6%, the value of the particular stock needs to be 166.67, going with this annuity concept. Similarly, one more numerical. What amount must you invest today? So invest today means I have to compute the present value at 6% interest. So I is coming out to 0.06 compounded annually. So K is 1 only here, so that we can withdraw 5,000, right? So I'm talking about withdrawing an amount of 5,000 at the beginning of the year. So it's an annuity due. So every year I want to withdraw 5,000 at the beginning of each year for the next 5 years. So N is 5. Again, it is beginning immediate. So there is no deferment period, and I am drawing it once in a year itself. So I can very well say N3 is nothing but 5,000 multiplied by annuity, where I is working out to 0.06. Then I have N, which is 5 years. And I am also now considering the type is not an immediate annuity, it's an annuity due. K I don't need to specify because it's once in a year. And even the M I don't need to specify because there is no deferment period. So with this it says if you deposit 22,325 right now and the annual interest rate is 6%. So right from the current period, right from the beginning of the current period, you would be able to withdraw 5,000 over the next 5 years. But if the same thing would have been an immediate annuity, the amount that I would require is slightly different. So if I have to withdraw at the end of the year, the first 5,000 I am withdrawing not at the beginning of the year but at the end of the year, then all I need is only 21,000 to withdraw 5,000 in each of the years. So this is how we can typically compute the present values of the annuities. Now even if you just extend it by giving a few more things, I say the k equal to 2. Let me just set k equal to 2, which means the payment is happening twice in a year. In this case, you have to deposit 21,373. If which means every 6 months the payment is getting made now. In this process, instead of the payment happening every year, so the overall it is 5,000 per year, right? Overall I am taking 5,000 per year, but the payment is happening every 6 months. In that case, which means after 6 months itself the amount is going up. Some amount is going up. So that's where I really require a slightly higher amount. So that is what is being specified as 21,373. So depending on how many times I am withdrawing, I would get a typical computation value out here, right? Then, now that we got an idea about the present value, the next thing we are talking about is accumulated value, which is nothing but the future value. If you see, AN is what I have called as the present value, which means as of today, what is the value of all the future payments. But if I am multiplying it with 1 plus I to the power n, it is nothing but I am taking this value to my final period. At the time the last installment is getting paid, I want to see if I want to withdraw the money at that particular point in time, what would be the amount that I am going to receive. So that is what we are calling as the accumulated value. So it's as good as if these are the different periods that I am talking of, different payments happening at each of these periods. If I find the value of all those payments as of today, it is called as the present value. If I find the value of all these payments as on the last payment date, this is what we are calling as the future value or the accumulated value. So how much is accumulated at the end of 5 years? So which is nothing but the annuity that I am getting, I am capitalizing it by multiplying with 1 plus I to the power n. I am putting a compound interest on the top of it. So it works out to be again another formula. The advantage is the formula is more or less similar to your annuity formula. All the inputs. The only thing is I have to give the formula as accumulated value instead of annuity. So I have to give the I value, which is the interest rate, N is the number of periods, then M is the deferment period if at all there is any, K is the number of times I am receiving or paying, making the payments, type is either immediate annuity or deferred annuity due. So the values are more or less similar in all the cases. So it's as good as saying, probably for the same N1 example, if I take, let me take the N1, right, 388. So I'll take N1 into 1 plus I to the power 5. Let me just take simply, I found N1 and I am taking it as 1 plus I to the power 5. So this number 598.47 is the accumulated value for that same numerical. So the other way of finding out the accumulated value without finding the annuity, which is generally the accumulated value is denoted by S. The present values of the annuity is denoted by A. Accumulated value is denoted by S. So I am calling it as S1. I'm not explaining the formula again because more or less the formula is the same. So I'll take it as accumulated value, wherein I'm setting the I is 0.09. The first example I'm taking, all others you can continue. The N is 5 for 5 years. I want to look at type is immediate. There is no deferment period and there are no multiple payments within the year. So based on this, if I compute S1, it is coming out exactly 5.98. I have to multiply it with 100. So this is where I'll get that 598 itself. So the concept of accumulated value is more or less the same. So if you quickly look at this numericals, what amount will accumulate if we deposit 5,000 at the beginning of each year, which is nothing but it's an annuity due for the next 5 years. Assume the interest rate is 6% compounded annually. So I can very well take accumulated value. So the I am taking it as 0.06. The N I'm talking about 5 years. The type of annuity is annuity due. So which is giving me that my S2 is 5.97. So this 5.97 I have to multiply it with 5,000. So which is giving me almost 29,876. So if you start depositing 5,000 per year right from now for the next 5 years, at the end of 5 years, you are going to receive 29,876 rupees. Similarly, a man wants to save 100,000. Okay, so his final amount needs to be 100,000 to pay. So look at the framing of the numerical, right? We are talking about 10 years time period. So here the amount needs to be 100,000. An education fund requires the investors to deposit equal installments annually. So every year he has to deposit some equal installment at the end of each year. So we don't know how much he has to deposit. So some X he has to deposit, and that X multiplied by annuity, regular annuity, whatever we are talking of. If the guaranteed interest rate, so this annuity is having I equal to 0.05, N equal to 10 years, and it is an immediate annuity, which is the regular annuity itself. How much does the man need to save each year to meet his target? So I have to find out this X. So which is nothing but 100,000 divided by whatever is the annuity amount that we are going to get. So which we are talking about the X, which is nothing but 100,000 divided by, so we are not talking about the annuity here. We are talking about the accumulated value. The accumulated value is becoming 100,000. So let me take the accumulated value, right? Because this X keeps accumulated to 100,000. So I'm talking about X is 100,000 divided by the accumulated value. So we can do two ways. I'll show both the ways. One using the accumulated value, two using the annuity as well. So when I'm using the accumulated value, the interest rate is 5%, the N is 10 years, and I'm saying the type of this particular annuity or accumulated value is an immediate. So which is saying that my X value is 7950.47. If I have to go with the annuity concept itself, yes, I'm going to receive 100,000 at the end of 10 years. What is the value as of today? I can find it as the present value also. So first let's do, if I have to use annuity, what is the way out? I'll find out the present value, right? So let me call P, which is nothing but I'm finding the present value of my cash flows in this present value, my cash flow is one single cash flow of 100,000. The time IDs that I have is 10 years. It's a lump sum thing. So I have a time ID of 10 years. The interest rates, this interest rates is going to be, what is the interest rate here? 5%. So when I'm giving this as the input, so the present value of 100,000 is coming out, which is 61,000. So 100,000 at the end of 10 years is same as 61,000 as of today. Now what I can do, I'll divide this 61,000, right, to get my to get how much I have to deposit. I'll divide this 61,000 by the annuity of I is 0.05. Then I'm taking N is 10 and type is immediate. Now this is another way I can solve this problem. All we need is clarity on the process. So even this is giving me that I have to save 7,950 every year over the next 10 years, so that the overall at the end of 10 years this amount is going to be 100,000, right? So this is the way we can solve different kinds of numericals that are associated with the annuities. I can find out the present values as well as the future values or accumulated values associated with each of these annuities, right? So now that we are comfortable doing the calculations involving annuities, we move on to the next, where the annuity amount may not be constant throughout, right? But it follows some kind of a pattern. So one of the most common patterns that could be existing with respect to annuity is it is either increasing arithmetically or decreasing arithmetically, which means instead of paying 100 every time, every year, the payment would go like this: 100, 120, 140, 160. So every period the payment is going on in this way. This is what we are calling as arithmetically increasing kind of an annuity. Or it would be decreasing: 500, 475, 450, and so on up to 100. So this is called as a decreasing annuity. This probably could be up to 500. This is called an increasing annuity. So for handling these kind of scenarios, and I want to find out again the present value associated with these kind of annuities, or in some cases I may want to find out the accumulated values for these kind of annuities. So those are the ones we are dealing with, increasing annuity or a decreasing annuity. Now we have the formulas again: increasing annuity. We also have a formula called decreasing annuity. Now the way we handle them is we try to segregate the parts. Let's take the numerical first. That would ease our understanding. The following payments are to be received: 500 at the end of first year, 520 at the end of second year, 540 at the end of third, and so on until the final payment is 800. So probably going with this, 800 would be at the end of the 16th year. So these are the payments that I am to receive. Use an annual effective interest rate of 2%, 0.02. Determine the present value of these payments at time 0. I want to find the present value of these payments. So this is where I try to see that this is an increasing annuity. Right? I am looking at this as an increasing annuity. Now what is that I can do for handling this is segregate out the constant part. So because 20 is the difference, generally what I suggest is from the first payment, subtract the common difference. So it is 20. So take it as 480. So basically write this as 480 plus 20 in the first year, 480 plus 40 in the second year, so on, 480 plus 320 in the 16th year. So there is a 480 for all the 16 years. So it would become 480 times the annuity, because 480 is a fixed amount. So I can take it as 480 times the annuity plus 20 is getting increased every period, 20, 40, 60. So 20 times I'll take it as the increasing annuity. This is how we solve finding out the present value scenario. So we'll break the whole data, pulling out separating out the annuity portion from the increasing annuity portion. So we'll do two separate calculations, one for the annuity, one for the increasing annuity, and finally we do the computation part. So this is for finding out the present value. Now the same thing, I want to find out the accumulated values at the time of last payment. So first let's finish off the annuity part. So there is for 450, it's an annual, 480, it's an annuity. For 20, it's an increasing annuity. Coming to this increasing annuity, I need to give the interest rate, then number of periods. So I know here it's 16 periods, and type. Immediate means the payment is being made at the end of the period. So I just need to give those three inputs quickly. Let me see. Immediate, sorry, increasing annuity. Increasing annuity. So increasing, oh, the spelling is wrong. Increasing annuity. So what is this increasing annuity containing? Function evaluates non-stochastic increasing annuities. Non-stochastic is it does not contain any kind of uncertainties. So fixed increasing annuities are typically computed. So as I have already indicated, it requires an interest rate, the number of periods, and either an immediate or a due kind of thing needs to be given as the input. So fair enough, let's give that. So for that numerical, I can say the PV1. So for 480, I'll take it as an annuity. So I'm taking annuity I equal to 0.02 for a period of 16 years, and the type is increasing, type is immediate. So this is the annuity portion for that 480, and I have for 20 I have increasing annuity. So I'll take it as increasing annuity with the same inputs. My I is 0.02, my N is 16 years, and the type again is immediate. So this is what I'm considering to find out the present value of this. So this gives me my PV1 is 8711, 8711. So if it is going to pay me 500 after 1 year, 520 after 2 years, 530 after 4, 540 after 3 years, and so on, increasing at the rate of 20 every year, then the present value of all those payments that I'm going to receive is equal to 8711. Or now the second question talks about find the accumulated value. Now if you want the accumulated value, just do a capitalization. So PV1 into 1 plus I is 0.02 to the power 16. I could have directly done this to find out the accumulated value at the end of 16 years. So at the end of 16 years, the accumulated value is going to be 11,988. But here also we can do the same thing. We can first use accumulated value for the constant portion. For the constant portion, I can use accumulated value, which means for 480, I can do the accumulated value separately using the accumulated formula. And for the 20, I have an increasing accumulated value, right? So that increasing accumulated value is actually obtained by this function called ISN. So let me see what this ISN is all about. Non-stochastic increasing annuities future value. So I can give the non-stochastic increasing annuities future value. So interest rate, the number of periods, again I have to give immediate or annuity due. So ISN is something that I can directly use for getting the accumulated value of the annuity. So this would have been, so I'll say AV1, which is the accumulated value. So initially I will take for the 480, I'll take the accumulated value formula because it's a regular annuity. Accumulated value giving the same I equal to 0.02, N equal to 16 and type is immediate. So this is my accumulated value for 480 and for the 20 I will use ISN increasing accumulated value. Again the same logic, I equal to 0.02, N equal to 16 and again the type is immediate. So by giving this as the input, I can very well get my AV1, which is more similar to doing a capitalization on the annuity value, that present value of the annuity that I have got. So either of the ways, I can use a combination of accumulated value and ISN, or I can use a combination of annuity and increasing annuity, and after that do a capitalization of the result that we have got. So for every problem, once the conceptual aspect is clear for us, we can very well have multiple ways of finding out the solution to that problem, just like this case that we are talking about, right? Fair enough. So this thing I think is comfortable. So let's move to the next. Now instead of arithmetically increasing or decreasing, in some cases I may see that the annuities might be increasing in a geometric progression. So instead of saying 100, 110, 120 kind of stuff, here we are talking about R 20. If it is increasing at 20, it is 100, 120, 140, 160. But going with the geometric progression, 100, 120, again 20% on this, 144, 20% on this, 172.8. So this is how, if it grows, the annuity, this is what we are calling that the annuity is growing at the geometric progression. So if the payment grows by some kind of percentage R and the interest value is I, then we are trying to adjust the interest rate by finding out a new interest rate J, which is nothing but 1 plus I by 1 plus R minus 1, which is otherwise, if you see, it is I minus R divided by 1 plus R. So either I do this kind of a setting, my J, which is the new interest rate, I can very well find out as I minus R by 1 plus R. Using this I can find out the new interest rate, right? And using this so if I am saying by whatever extent my interest rate, my value is payment is increasing, if I am taking it as R and if the interest rate is I can very well consider the J, which is the new modified interest rate, I will take it as 1 by I minus R by 1 plus R, and based on that I will proceed with my calculation. Right, instead of I now, I would be taking this J, which is arrived at by 1 I minus R by 1 plus R. So look at this example, an annual annuity due. So we are talking about an annuity due. So the type we are setting it as due. Pays $1 at the beginning of the first year. So it's a due. What is paid is $1, right? Each subsequent payment is 5% greater than the preceding payment. So the payment is growing at the rate of R, which is 5%. So R is coming out as 5%. The last payment is at the beginning of the 10th year. So N for me is 10. Calculate the present value using an annual effective interest rate of 4%. So I is coming out as 4%. So now based on this I can find out my J, which is nothing but I minus R, right? So I can find out my J as I minus R. I is 4%, R is 5%. So minus 1% divided by 1.05. So that is what is coming out as J. So based on this J, I am trying to find out the present value, right? So this is how we are adjusting the I based on the R that we are getting. So let me try finding it out. First let me compute my J, which is nothing but I minus J. I is 0.04 minus R 0.05 divided by 1 plus R 1.05. 1 plus 0.05. So this is what is coming out as my value of J. Then if I want to find out the present value of this annuity, let me call it as PV2. So the amount is 1. Then I need to find the annuity here. It goes everything the same way. Now I will directly take it as J, which is my new interest rate. Then N, I'll take it as 10 years, and type, I'll take it as annuity due. So I'll take it as due. So based on this, I'm getting my PV2, which is working out to 10.44. So if the amounts are increasing at this particular rate at 5% every year, my interest rate is 4%. So whatever the ones that are typically deposited at the end of each period, 1 and 1.05, 1.05 squared, something like that, if whatever is getting deposited at the end of each of the period, the present value of all those payments put together is working out to 10.44. So that's how I can typically compute the present values, or even I can do the accumulation also. Once I know the present value multiplied by 1 plus I to the power 10, I'll get the accumulated value. The only thing is here, I don't need to separately look at increasing annuity or decreasing annuity. Adjust the interest rate. If it is growing at a geometric progression rate, just adjust the interest rate. Use that modified interest rate instead of the original interest rate. That will solve the numerical completely. Right? So that's how we are addressing problems of this kind. Then, the other scenario that we generally encounter is the deferred annuity. The annuity is not starting in this year. So in this year itself, if it is at the beginning of the period, we call it as annuity due. If it is at the end of the period, we are calling it as immediate annuity or regular annuity. This is what we have been using. But in some cases, the starting date of the annuity is not in the current period. neither at the beginning of the current period nor at the end of the current period. The starting date is at a future date, not these two, but sometime later than the ending of the current period, probably a couple of periods later. In that case, we call this kind of annuities as deferred annuities. Everything is the same annuity formula, the same accumulated value formula, we'll use the same things. The only thing is in that there is a parameter called M, which we would be setting it to whatever the time period. If you look at it here, calculate the present value of an annuity due. So the type is due here. Pays an annual amount of 1200. So the X, which is 1200 for 12 years. So N is 12 with its first payment 2 years from now. So we are talking about an annuity, a deferment period of 2 years. So we'll set M equal to 2. The effective annual interest rate is 0.06, which is 6%. So this is how I can treat it as annuity due and solve the problem. But how will I solve it as immediate annuity? If I am looking at it as immediate annuity, what is the difference now? Instead of paying at the end of the beginning of the period, we'll talk about this payment being made at the end of the period. So we are talking of n equal to 12 itself, but we'll set m equal to 1. So for the next year, the beginning of the second year is nothing but the end of the first year. So that's where I'll set m equal to 1, all else remaining the same. I should get the same answer if I'm going with immediate annuity and setting m equal to 1, or an annuity due setting m equal to 2. Either of the ways. So let me try out. Right. So we are talking about deferred annuity. So I'm calling it as DA1. So it's nothing but 1200 times I'm taking the annuity formula, wherein my annual interest rate is coming out to 6%. The number of years, we are talking of 12 years. Now here I have to set which is the deferment period to 2 periods. I'll set my deferment period to 2, and if I'm setting it to 2, then the type will be annuity due itself. But if I'm setting it to 1, the type will be immediate annuity. So I am finding out TA1, which is giving me 9491. The same logic, if I change this from due to immediate and I change this from 2 to 1, then also the result should be the same, which is giving me the same 9491. So conceptually I need to have a clarity on how I can handle, because there are multiple ways of solving the problem. So all we need to be comfortable with is coming out with the proper timing for the whole thing, right? So that's how we are handling the deferred annuities problem. So now that we have dealt different kinds of conceptual aspects, right? We have looked at right from one single individual payments, NPVs, IRRs, annuities, increasing annuities, deferred annuities, decreasing annuities, proportionally growing geometric annuities growing at geometric progression. So with so many such kind of examples, right? The basic conceptual aspects being clear, the formulas of R being clear, the functions of R being clear to handle all these aspects. Now we are in a position to really solve some kind of practical application which are involving all these conceptual aspects. Coming to the usages of this financial mathematics, we see a lot of applications in pricing of the bonds. We see in loan amortizations. We also see there are various bonds and the risk measurement of the bonds using duration, using convexity. So there are many practical applications in the world of equities, in the world of bonds. Almost every financial instrument that we are talking of the valuation of that financial instrument typically goes with the present value computation itself. The present value of the future expected cash flows. That's the typical fundamental that we are using for any kind of financial instrument pricing or valuation. So we need to have a good amount of understanding on this. So that's where I have taken some simple examples to start with. So if I have to do the computation of the price of the bond, how will I use all this knowledge that I have gained with the calculations of the present values, the annuities, etc. So right, let's try to understand it. So I'm talking about a 5-year bond, right? N is 5. It offers 3% coupon. So coupon is some fixed amount that the bond pays every year. The par value of the bond is 100. So which is the final value, which is what we are calling as the par value. The final value is going to be 100 for this particular bond, right? The coupon is 3% of that, which is 3. But this 3 is paid twice a year. So which means it is 1.5 that is paid every 6 months. So the coupon is quoted as annual coupon, but it is paid 6 months, every 6 months, which is telling me that it is 1.5 every month. So I have to use an annual effective rate of 5% and find out the price. Now, which means if I look at the cash flows that I'm getting, so 3 is coming in the first year, 3 is coming in the second, 3 is coming in the third, 3 is coming in the fourth, and also 3 is coming 3 is coming in the fifth, along with a principal value of 100 that is coming in the fifth year, right? So for 5 years this 3 is looking like an annuity, but the payment is happening twice a year. So I can set K equal to 2 in my annuity. In my annuity till now we did not use K. It was taking a default of 1, which means the payment would be made only once in a year. But here, because the bond payments are happening twice, I can very well take that the payments are being done twice a year. Rest all remaining the same. The payment is being made at the end of the year. So corresponding to this 3, right, corresponding to this 3, I can treat it as an annuity, right, wherein my I is 5%, my N is 5 years, K is 2, where the payments will be made 2 times a year, M I don't need to consider, no deferment period, and this is an immediate annuity. So the type is immediate. So this is how, corresponding to all the 3's that I am getting, I'll handle it. Now 100 is a lump sum. So I can very well find the present value associated with this lump sum using the present value formula. I'll find out the present value formula where I is 0.05, N is 5, right? And now this is not an annuity. So my cash flow, I have to give cash flow which is 100. So I give these things, I'll get the present value corresponding to this 100, which is the lump sum amount. Corresponding to these annuities, I will do this one. Finally, it will give me the bond price. So the present value of all these future cash flows that we are going to receive is what is the price of the bond. So I'll call this as bond price. The first thing regarding the redemption amount, par value, 100 I am going to receive on maturity. So I am calling it as 100 times present value computation. The cash flows, right? I have to give cash flows is equal to 100 on single value times time IDs. I can give it as after 5 years. and I have to give interest rates is equal to point, what is the interest rate? 5%, 0.05. So based on this, I'll get the present value of this 100. Along with that, I'll take the annuity also. So I'm taking it as annuity. For this annuity, my I value is 0.05 and N is 5 years. Type is immediate because the payments are being made at the end of the period, not the beginning. K, I will set it equal to 2 because the payments are being made twice a year. So this entire annuity, I'll multiply it with 3 because 3 is an amount that is following this particular process. So based on this, let's see what is the value of BP, which is nothing but the value of this bond. Why is it coming out to 7,800? Oh, I don't need 100 into here, right? Because I have already considered in PV, I have taken the cash flow, right? Cash flow, I have already taken it as 100, so I should not multiply it by 100 again. That is what is the mistake. So I'm directly taking the present value. Only for annuity I'm doing the multiplication because annuity takes that it's a present value of $1 that you are going to receive at different points in time in future. So based on that, if I look at the bond price, it's coming out to 91.5. So for this particular bond, which is going to pay me 3% coupon every year, that too the payments being made twice a year, par value being 100, and the maturity of the bond being a 5-year bond. And if I want to find out the present value using an annual effective interest rate of 5%, it works out to 91.5. So if the bond is available for, so that is the value of the bond as per its features. Now, if the bond is available in the market for lesser than 91.5, I can very well go ahead and purchase the bond. But if it is available for more than 91.5, I would not be interested in purchasing the bond. I might very well drop off from the purchase of the bond. So that's how we can do bond pricing using the present value as well as the annuity functions that we have learned as a part of this time value of money. Then let's take up another example in this context. Loan amortization. We are talking about a 10,000 loan is stipulated with 7% annual interest rate, right? Annualized periodic rate. So we are talking about the loan amount X equal to 10,000 bucks. The interest rate we are taking it as 7%, and there are monthly installments. So my K is coming out to be 12. I'm talking about a monthly installment here. Find the monthly installment if the loan is planned to be repaid in 5 years. So my N is 5 years, and I want to prepare a table for the entire 60 months. So basically it's like 10,000 is the total loan amount, right? So typically the present value, or because it's an annuity, the annuity going with this scenario, gives me some amount to be typically paid for one. But what we are talking of is the entire 10,000 corresponding to 10,000. I want to find out what is the value of this particular annuity. And that would give me the annuity associated with 1 year, how much I have to pay. So based on that, if I am finding out for Month means I have to divide this annuity value by 12. So if you are trying, so basically it's like I'm paying some installment, right? So probably think of this like this: some A value, some amount A value I have to pay, right? This A value, when I'm multiplying it with the annuity factor, this A value when I'm multiplying it with the annuity factor, which is taking 0.07, and I'm talking about 5 years, k equal to 12, immediate kind of scenario, right? So this A value multiplied with this. Now this A is the total yearly amount. Now we are asking for a monthly amount. So this A I am calling it as 12M. So M is the monthly amount. So 12M multiplied by this annuity factor will be equal to 10,000. So basically now M for me comes out as 10,000 divided by this annuity factor as well as by 12. So this would give me what should be the monthly installment that I have to make. So I can call EMI as 10,000 divided by the annuity factor I need to consider. So let me take annuity I equal to 0.07, N equal to 5 years, K equal to 12 because it's a monthly installment that we are talking of, type equal to immediate, and there is no deferment period, so I don't need to bother about that deferment. So whatever this computation that is coming out, I'll divide it by 12. So based on that, I'm getting my EMI value as approximately 197. So this is the EMI that I have to pay every month over the next 5 years. So basically if you are looking at how much you are paying, I'll multiply the EMI with 60 because every month you are paying almost 197. So overall for that 10,000 loan that you have taken, you would be paying 11,819 bucks. But in some cases, I might be interested in preparing a table for the entire 60 months, which is what we typically call as amortization table, right? How much EMI we are paying corresponding to what is the interest part, what is the principal part. We want to do that kind of a table kind of stuff. So let's take the table, right? So initially, let me initialize a few variables. So first let me take the end balance, ending balance, right? Or probably let me take the ending balance as a numeric variable with 60 placeholders, right? It's an array containing 60 observations. So for each of the period, I want to consider one ending balance. So I'm taking the ending balance as one numerical variable. Then I'll take the opening balance as also another numeric variable with 60. Similarly, the interest portion of it, right? I'll take it as another numeric with 60, and principal part of it, I'll take it as numeric with 60. So each one of the variables I am considering to be an array with 60 because I have to prepare a table for 60 periods. Okay, so we have set these initial values. So I can very well say the opening balance, right? I'll take the opening balance of 1. I will set it as opening balance of 1. I will set it as the total principal amount, which is 10,000, right? And so for all the initial ones, for interest of 1, I will set it as opening balance of 1, interest of 1, I am setting it as opening balance of 1 multiplied by whatever is the interest rate, right? So the interest of 1, the interest rate is typically what is the interest rate? 0.07 by 12. So this is the interest of 1. Then principal of 1 comes out as the total EMI, whatever we have got, EMI minus the principal interest of 1. Let's first test out for 1, then we'll go ahead, right? So EMI minus the interest of 1, and what else? Principal is there. Then we have ending balance, which is working out as the OB ending balance of 1 is working out as the opening balance of 1 minus the principal of 1. So let's see whether all the calculations have been taken care or not. So let me put OB of 1 coming out as 10,000. I'm taking interest of 1 coming out as 58.33. Alright. Then principal of 1 should come as the balance, which is 138.66, and ending balance of 1 is coming out as 9,861. So this is what is coming out as the numbers across 9,861, because it is coming out as OB1 minus the principal of 1. Fair enough. Now we will do it from 2 onwards. For I in 2 to 60, so this is what I am looking at for my I in 2 to 60. So each one I have to take it one by one. For I in 2 to 60, I am considering the first thing, the opening balance of I. Opening balance of I is same as ending balance of I minus 1. So this is what will come out as the opening balance of I. It will come out as ending balance of I minus 1. The interest of I will come out as opening balance of I multiplied by 0.07 by 12. This is what will come out as interest of I. Then principal of I will come out as EMI minus the interest of I, and it comes out as the closing balance. Ending balance is a critical one. Ending balance of I comes out as opening balance of I minus principal of I. This will come out as the ending balance of I. So based on this, I am looking out, and we also require the EMI, right? EMI of I. Let me take another column called EMI. So EMI of I is always the same as EMI. right? So let me close this. So I'll say warnings to see these warnings. Okay, it's warnings itself, fair enough. So I can set EMI of 1 also to be equal to EMI. So I have all the runs. Okay. So EMI also, let me set it as numeric 60. Then I can set EMI of 1, etc. So I'm setting EMI also as numeric. Now I can call it as amortization schedule, right? Let me call it as amort shed, wherein I'm putting, I require a data frame now. So I'll consider all of them as a part of the data frame. So initially I will set month equal to 1 to 60. I'll simply repeat the process. Then the EMI, right? I'm setting the EMI as the EMI values. Then probably if required I can round that EMI, or let me take the EMI as it is. Then I can take the opening balance, open I'll call it, which is like OB, and I'm also having interest, I'm calling it as INT. Then principal, I'm calling it as PRI, and finally close, which is the closing balance, I'm calling it as EB. So based on this, I'm creating a data frame called amort schedule. So let me see what comes in amort schedule. Wow, I'm getting a kind of a table which is telling me for each of the months what is my opening balance. So EMI is coming out as 0. So EMI did not come out properly, but let me see opening balance. Okay, everywhere this is principal is keeping on increasing, interest is keeping on decreasing, right? EMI. Okay. So what we can very well do is amort schedule dollar EMI. Let me assign it to EMI value. Now let me see what it comes out. Amort get. So what is the EMI value that we are getting? Oh, EMI is coming out to be 0. Why is EMI coming? Okay, this is the EMI. This is where the problem is. So I have to do the EMI computation again. So let me do the EMI computation again, and then let me allot this EMI value. Right, it's just a variable got overwritten. So let me call this EMI again as this one. So now let me do the allotment. Now let me see amort sketch. Yeah. So this looks much better. Right, the principal at the end of 6 years is going to be at the end of 60 months. So this is the principal contribution each of the periods. So this is the first month. From the second month, this is the opening balance, this is the interest portion of it, this is the principal portion, and the closing balance is coming out as 9861 minus 3139. So this process is keeping on going on. So that's how the closing balance is completely getting reduced and reduced. So this is what typically is happening as a part of this amortization schedule computation. So I can have the amortization schedule created for the entire period, and based on the interest, based on the principals, I could see how the principal is growing, how the interest is growing, and which is what will result in what would be the typical payment that is pending from the process. So that's how the ending balance, the beginning opening balance, all these things, this is what we are calling as the amortization schedule, right? So this is what is coming out as a part of the amortization schedule, which is what we could typically use it for all the display purposes. So if you say after 1 year, what is the loan amount that is still outstanding? 8,281 is still outstanding at the end of 12 months. So that's how I could typically try computing the amortization schedule. So here, once we understand the basic functionality of our basic structure of the data frames and various aspects of R, the definition of the arrays, etc., creating these kind of tables would be a much simpler task itself. Then, one more important application regarding the same, we are talking about the duration and convexity of a bond, generally taken as the measures of risk associated with a particular bond. Duration and convexity are more and more important features while defining the risk that is associated with a bond. So if you just type in question mark duration, you'll see that this function evaluates the duration or even the convexity of a series of cash flows. So when you are saying duration, I have to specify all the cash flows that I am going to get from this bond. I have to specify the time IDs that are going to come at different points in time. I have to specify R, which is the nominal kind of an interest compounded mthly. So I have to specify the nominal interest rate, which is in the form of I. Then what is the frequency of payments? I have to specify it in terms of K, the payment frequency or the compounding frequency. In this duration, again, I am not talking about the theory of it. In the duration, we have something called Macaulay duration or the effective duration. There are two different ways of computing the duration. So the Macaulay duration is taken as the weighted average of the present value of the cash flows. So when we talk about the Macaulay duration, it is purely based on the weighted average on the present value of the cash flows, where the weights are based on the timing. So it's basically like the different times, the different cash flows are being received. I take the present value of all the cash flows. The weights are, the timings are multiplied with the present, the weights that are given based on the present value of the cash flows. That is what we are calling as the Macaulay duration, and the effective duration is nothing but the percentage change in the price of the bond with respect to a change in the interest rate. So there are different computations of the duration. So we can see the difference could be very small, but these are the two different ones. So that's where I have to specify whether the Macaulay is true or not. When it comes to convexity, we just need to give the cash flows. Typically convexity is called as a second order measure of the riskiness of the bond. I'm not going into the theoretical depth of it. Again, I have to give all remaining the same, only there is nothing called Macaulay versus effective here. So these two, we say that we can measure the risk of the bond. The higher is the duration, the higher is the interest rate risk that is associated with the bond. And using this duration as well as convexity, we can even predict what could be the price of the bond if the interest rate changes by some percentage. So for both the purposes, these are typically used. So let's see how we can use duration for this typical example. So the example is compute the duration and convexity of that previous bond that we have talked of. Right, we'll talk about the semi-annual payment or annual payment, whatever it is. So in this case, the cash flows for me are 3 at the end of 3 in the first year, 3 in the second year, 3 in the third year, 3 in the fourth, and 103 in the fifth year. So these are the cash flows. Then I'm talking about the time, right? The time intervals. We are talking about 1 to 5. So these are the time IDs that I'm giving. So based on this, I can find out the duration. First, let's find out the Macaulay duration. Then we'll try to find out the effective duration as well. So the cash flows, for finding out this duration, the cash flows I'll call it as CF. Then time IDs, I'll take it as TI. The interest rate, I've got it as one single number 0.05. And here the payment, right? If I have to take the previous example itself, the K is 2, the payments are being made semi-annually, the coupon payments are being made semi-annually. And let's say I want Macaulay duration, I'll set it to true. If I want effective duration, I'll set it to false. So I'll call this as Macaulay duration. I'll call this as Macaulay duration, which is working out to 9.17. Why is it coming out to 9.17? Cash flows are this. Oh, I have to specify the cash flows for each of the periods separately. Looks like. So basically, let me change the cash flows now. So it is 1.5 in each of the periods. So let me call it as rep 1.5 9 times, and along with that let me call 101.5. So these are the CFs. So let me see what the CFs are. Yeah, this is how we are getting. No. The times are not matching. K equal to 1 frequency, compounding frequency for the nominal interest rate. The cash flows representing the cash flow amounts. Okay, so I think it was the original case itself, the initial case itself, CF. I'll take this. Based on this, I'll compute my modified duration or Macaulay duration. So this Macaulay duration, I have to divide it by 2 because we are talking about 2 periods. So the Macaulay duration is coming out to 4.58 here. Whereas when I go with the annual payment instead of semi-annual payment, I'll set this K equal to 1. In this case, the Macaulay duration is going to come out to 4.47. So if the payment is typically being made at the end of the year, the Macaulay duration is going to be 4.47, but if it is being made twice, the Macaulay duration is coming out to be 4.58. Then we are talking about effective duration. So I'll set the Macaulay equal to false instead of true. This is what will give me the effective duration. So in this case, it comes out to 4.70. So that's how our durations based on duration is changing, and this effective duration is a measure of the interest rate risk present in the bond. So I can find out the interest rate risk of this bond going with 4.70 as the value. And now if I want convexity, I can go with the convexity associated with this bond, wherein I am setting the cash flows of this bond as CF, the time IDs I am setting as TI, then I am taking it as 0.05, and K I am setting it as 1. In this case, I am getting my convexity associated with the bond. So convexity is coming out to be this much. Again, we have formulas which talk about how do I really compute the bond price if the interest rate changes by 1%, half a percent, 0.25% up or down based on the interest rate, based on the duration as well as the convexity. So we have different kinds of calculations which use the present value concept, the cash flows, the annuities. So once we are comfortable with understanding all these concepts, a lot of numericals can quite comfortably be worked out. A lot of financial mathematics can quite comfortably be evaluated both for equities or fixed income securities, or for that matter any kind of investments. The value of majority of the investments goes with the understanding of the present value concept itself. So these are the various things that you should be comfortable with. I hope we have dealt a good amount of time in terms of understanding all these aspects. If you have any further queries regarding any of these topics, handling them, the conceptual part of it, or even handling those functions in R, you can very well get back to me by giving me a call on the number that I have provided below, or you can even send in an email at the email address that is provided there. Thanks a lot for listening to this session. Thank you very much.